Well, see, in the last lecture we have I have discussed some of the chemical reaction of glucose, which can be justified with the open chain structure as well as cyclic structure. But if you see here that these reactions, see, this is if I classify, this is one observation. This is a second observation, and this is a third observation, and this is fourth observation, and very important, this is fifth observation. So all these observations, all above reactions 1 to 5 suggests that the glucose exists in cyclic structure, that is, do not have free CHO group, CHO oblique CO group, aldehydic or ketonic group, right? So all these observations, they suggest that glucose exists in a cyclic structure and do not have free, this is very important, free CHO or CO group. Okay. Now see another observation, Muta rotation. Okay. See this Muta rotation. This is one of the physical observation, physical property, which also suggests that this glucose molecule exists in the cyclic form, right? Let's see, what is this Muta rotation? If you take pure glucose and prepare its aqueous solution, aqueous solution, and you know, this is optically active compound. This glucose is optically active compound, so measure the optical rotation, right? Measure the optical rotation. So this, what, take the pure glucose crystals, prepare its solution, and immediately measure the optical rotation. You know, you will find what observation you are getting. The observation is this freshly prepared solution, aqueous solution, this shows two optical rotation, shows two different optical rotation, different angle of rotation, One is 112 degree and other is 18 degree. So when you prepare pure glucose aqueous solution, so what you will observe when you observe this optical rotation, optical activity by polarimeter, so you will observe that this freshly prepared solution shows two different angle of rotation. And one more important point, that this angle of rotation is not constant. This will change with time. So this change in optical rotation of any optically active compound with time, this is called Muta rotation. right? So the definition of Muta rotation is the change in change of angle of rotation of freshly prepared solution of glucose is known as Muta rotation. So one angle of rotation is 112 degree, second is 18 degree. Now this will changes to 52 degree, 54 degree, and this also changes to 54 degree. So this is the observation, right? So this Muta rotation, it is the change in the angle of rotation of freshly prepared solution of glucose with time, right? And finally, it will attain the equilibrium, and this property is known as what? Muta rotation. So this property of carbohydrates or of this glucose cannot be explained by open chain structure. You know what this suggests, what the inference we can draw from this, that if we take freshly prepared or if we take pure glucose, definitely it is the mixture of two isomers. Otherwise we don't get this two different angle of rotation. So this is T is equal to 0 and T is equal to 0, two different, and this is T equilibrium, right? So this observation suggests that pure glucose molecule has two isomers, isomer 1 and isomer 2, and this you cannot identify, or you cannot justify with that open chain structure. So this is very strong evidence for this cyclic structure, right? Now let's see, and this Muta rotation is also the property of reducing sugars. This is also because later on it is observed that all reducing sugar shows this property. So this is Muta rotation is the characteristic property of reducing sugars, right? So I will discuss in detail regarding this reducing sugar, but first we will see how this cyclic structure and cyclic structure and other properties of this glucose can be explained. So all of you are knowing that if you take this aldehyde, right? So if if you take this CH3OH and HCl gas, so here you will get OCH3 and OH, R and H. This is hemiacetal. All of you are well known to this reaction, so I am not going to spend much time here, and further it will require 1 mole more methyl alcohol so that it is converted into acetal. R and H. So this is the simple reaction all of you are knowing, right? This is acetal. So 2 moles of alcohols are required to form acetal from aldehyde or from ketone, right? How many moles? 2 moles of alcohol, methyl alcohol are required, right? Now see, if you have a structure like this, suppose that this aldehyde group and alcoholic group both are present in the same molecule. So 1, 2, 3, 4, 5. So it is always a good habit whenever you have such type of bifunctional or trifunctional groups are present in the same chain. So it is a good habit to put number first. After that you will do your chemistry. So if we take HCl here, so what the possibility is there that this OH, first this will form a ring with this carbon and form a cyclic hemiacetal. After that, only 1 mole of methyl alcohol is required to complete the acetal. So what will happen, this lone pair, this will attack here, this will go like this. So how many membered ring? 1, 2, 3, 4, 5. 5 membered ring you will get, including oxygen, like this, right? What the number? This is number 5. This is number 5. 5 attached with 4. 4 with 3. 3 with 2. 2 with 1. And this carbon is carbon number 1, and OH is attached here, and this is here. So if you examine this, you will find that, see, this is a ether linkage, and this is alcoholic linkage. So alcoholic group, so alcoholic and ether, both the functional groups are present at the same carbon. So this is called cyclic hemiacetal. This is cyclic hemiacetal. And now if you want, then you can convert this into the complete acetal with only 1 mole of alcohol. So this time you will get acetal. Right? So you know, this is hemiacetal, and this is acetal, and this is formed by the only 1 mole of alcohol. So if you examine the glucose open chain structure of glucose, then you will find that, okay, in the same molecule you have CHO group and so many OH groups are there. So there is a possibility that this internal reaction will take place in glucose so that OH and CHO will react first to produce this hemiacetal cyclic structure, and after that this will react with only 1 mole of alcohol and give the acetal, right? So this is cyclic acetal, and all of you are knowing that if oxygen is present in the 5-membered ring, then this is called what? Furan ring. Furan. And all of you are knowing that this in carbohydrate chemistry, OSE suffix we are supposed to use. So this type of structure you can say furanose structure, right? So this is skeleton of furan, although it is not furan. Furan should have this type of, but this bare ring is type of furan ring, right? So this is the formation of cyclic hemiacetal and acetal. Okay. Similarly, if you have this type of structure, this type of so if you put a number 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6, right? So if you take 6 carbon chain with alcoholic group and this, so they will condensed and produces right. So this is a 6-membered ring containing oxygen. This is called pyron ring. This is called pyron ring. So this is OSE, so called pyranose ring. And you know this OH group and this group is present here. So this is a hemiacetal, cyclic, and one more thing is there. See this ether linkage cyclic. So this linkage is also termed as a intra-glycosidic linkage. This linkage is called intra-glycosidic linkage. Intra-glycosidic linkage. Intra-glycosidic linkage. So this linkage OCO this linkage, this part only. This is called intra-glycosidic, and sometimes you may get interglycosidic linkage as well, right? So now it is clear to all of you that why this glucose molecule suppose that now you are given that glucose and 1 mole of methyl alcohol, 1 mole of methyl alcohol, and you get complete acetal, means glucose exists in this form, right? Means the glucose already exists in this form, then only you will get complete acetal from 1 mole of methyl alcohol, right? Now see, if you react this compound with methyl alcohol and HCl, so you will get complete acetal. This is the acetal, right? So how this is, converted? First, glucose first converted into hemiacetal form, and after that this will convert into the acetal form, right? Clear to everybody? Okay, good. So now I have some questions for you. And see, this is homework for you people. Draw the cyclic hemiacetal that is formed when each of the following bifunctional compound is treated with not aqueous acid. You should take here HCl gas, right? So all of you should make the hemiacetal, cyclic hemiacetal, and then let me know, right? So do this in the form of homework. Okay. Now see, one more question. Suppose that now see this question. So for each of the following pair of compounds, determine whether they are enantiomers, epimers, diastereomers that are not epimers, right? Diastereomers means that are not epimers or identical compounds, right? So see first, if you examine first compound, CHO, same functional group. See here, OH this side, right hand side in the Fisher projection, then OH in the left hand side, and OH left, OH right, CH2OH means the only one carbon has the different in the orientation. So definitely these two compounds are what? Epimers. Right? Now come to this. See here, OH right hand side, OH left hand side, OH left hand side, OH left hand side, OH right hand side, OH right hand side, OH right hand side, sorry, OH right hand side, OH left hand side, OH right hand side, right hand side. So in this case, you have two carbon at which the orientation is different. Now tell me, is it included in the definition of epimer? No. In epimers, only one carbon orientation is different. Here, two carbon OH orientation is different, so they are diastereomers. So basically, if you see that these two compounds has no mirror relation. So broadly they are classified as a diastereomers. But this a special naming is used in the carbohydrate chemistry, that is epimer. So epimers, if you see broadly, are basically they are part of diastereomers, but you cannot write here in carbohydrate chemistry them as a diastereomers. You have to write epimers, right? Now see this compound CHO, CHO, OH this side, OH this side, OH this side, so OH this side. So if you put a mirror image, mirror here, so you will find that these are the mirror images which are non-superimposable. So definitely they are enantiomers. Enantiomers. Right. Now see this question. This is still I have not taught you, so this is homework, right? This is homework. Definitely in the same lecture or in the coming lecture, I will definitely teach you what relation they have, how to identify, right? Now let's see, let's do some work on this cyclic structure of glucose. Very focused, very careful. All of you should see how to make this glucose, cyclic structure of glucose, right? So everybody should focus here. If you miss, definitely you will not understand the concept, right? See, CH2OH. OH, OH, H, H, OH, H, OH, H. Right. So this is the glucose structure of glucose. Now tell me, this is the aldehyde group. If you make a ring interglycosidic linkage or hemiacetal formation between this oxygen and this carbon, so you will have 1, 2, 3. You will get 3-membered ring. Okay, you will get how 3-membered, right? If you make a reaction between this and this carbon, so 1, 2, 3, 4, you will get 4-membered ring. If you do the reaction between this oxygen 1, 2, 3, 4, 5, then you will get 5-membered ring. But if you do the reaction between this OH 1, 2, 3, 4, 5 and 6, so you will get 6-membered ring. Now let me know which OH group condense with this CHO group react with this to form a hemiacetal. So all of you have enough information regarding the stability and formation of cyclic structure. So definitely there is a reaction between C1 and C5. C1 and C5, they will react with each other, means this oxygen, this will react with this carbon. See, this is 1, this is 2, this is 3, this is 4, and this is 5, and this is 6, right? So there is a reaction between this carbon and this oxygen. Okay, getting my point? So this oxygen and this carbon, so that you will get 6-membered ring. So now I'm see, this chemistry, carbohydrate chemistry is so important, and you can say we can say that so sensitive that you cannot make any OH from this side to this side, or it is not I mean, arbitrarily we can draw the structure. You have to very careful to draw the cyclic structure. So I am giving you idea and trick how to make the perfect cyclic structure of glucose. What you do, this structure, you make it rotate this molecule clockwise. And after making rotation, you have to make this folding at the different carbon. So see, I am doing this. See this carbon number 1 I am making here. See here. C double bond O H. And I am making 6-membered pyranose ring flat structure. So I am doing folding here like this. It's very simple. You have to make this orientation like this. Now this is carbon number 1. This is a planar structure. Now this carbon number 2, OH will go down in this flat structure. Then carbon number 3, OH will go up like this. I am not showing here H. Number 4, OH is going down. Right? And number 5, OH is coming down. And if you are writing OH coming down, so H is coming up, and here CH2OH. Hopefully this is up to this point everybody is clear. 1, 2, 3, 4, 5, 6. You know this carbon is stereogenic. Carbon number 5 is stereogenic. There is a reaction between this. There is a reaction between this OH and this carbon. 5 OH, not 6 OH. If you make the reaction between this, then you will get how many membered rings? 6, and this one 7. 7 membered ring you will get. So this is not 7 membered ring. So this OH reacts with this. So since it is stereogenic carbon, if you directly change this OH and this CH2OH, structure will change, configuration of this carbon will change. So you have to be extra careful that the configuration of this carbon should not change. So what I have told you in the stereochemistry, that at any stereogenic carbon, if you do the 2 exchanges in the R and S nomenclature I have taught you, that if you make 2 changes at any stereogenic carbon, then the configuration remains same. So what you want to do, you wanted this OH here. So what you have to do, first you should make the exchange of H with CH2OH, put this CH2OH here and H here. After that, make the changes between H and OH. So put OH here and H here, right? So this will give you the carbon number 5 without changing the configuration, right? So what operation we are going to do here? First we exchange H with CH2OH. Then this is a 90-degree exchange, we can say. Then further exchange H with OH. So these 2 exchanges will leave no change in the configuration of the carbon number 5, right? So I am doing this operation here on this molecule. So these two operations H will come here, CH2OH will come here. You cannot directly write like this. If you are, remember, then there is no problem. But if you are doing with, concept wise, then OH, right? Like this. Okay. So now your molecule and groups in your molecule are so perfectly oriented that they can react, and the configuration in this molecule and in this cyclic structure have no change, right? Now see, again think wisely here. This is sp2 hybridized planar structure, so there is two possibilities that this OH will attack from this side and from back side. So there are two possibilities here. There are two possibilities, right? Front attack of OH and back attack of OH. So I am keeping OH from the same side and I am doing this OH orientation different. So see, reaction between these OH, H and CH2OH, OH, OH, OH. And another structure is possible that this OH this side and H this side. See, very remarkable point here that uh, this is stereogenic, this is stereogenic, this is stereogenic, this is stereogenic. So in open chain structure, if you see, you have 4 stereogenic carbon, 1, 2, 3, and 4. But now in cyclic structure, you have one more stereogenic carbon. This carbon